Oh, okay. So we're going to see now I'm hot. We're going to prove this assertion that solutions to Laplace's equation have this property that the average over the surface of a sphere is equal to the value at the center. And the way we'll do that is, well, we'll basically assume we know that certainly the potential of a point charge is a solution to Laplace's equation if you're outside the charge. And because remember, Laplace's equation is just Gauss's law in a charge-free region written in terms of the potential. So as long as you're not right on top of the point charge, you are in fact in a charge-free region. And so the potential of the point charge is a solution of Laplace's equation. And we'll assume that any solution of Laplace's equation can be written as a sum of point charge solutions or integral over little dq's. In other words, we'll assume that there's no mysterious solutions of Laplace's equation that are from outside the realm of electrostatics, that what we've got here is perfectly general. And so we will, following the principle that you put the center first and then draw the sphere around it, which isn't actually the principle, but it's the one I just followed here, then what we'll do is we'll show that the average of the potential due to a point charge over the surface of a sphere where the point charge lies outside the sphere is in fact equal to the value of the potential at the center. And so we'll take a little patch on the surface of the sphere whose radius is r, and we'll put the point charge on the z-axis. It doesn't give any loss of generality because obviously we can just define the z-axis to be the direction from the center of the sphere to the point charge. And as usual, we'll make our beloved script r be the distance from the source point to the field point, which in this case is our little patch. So we're going to average v over the surface of that sphere, v due to the point charge, show that it's equal to the value at the center. So everybody on board with what we're doing here? Right? Happy with what we're about to do, or at least you know what we're about to do. So we'll say that our point charge lies at z equals z naught, and then we'll note that if we are going to find the average of some function, then we do that in terms of an integral. Right? If you average a function, you do an integral in order to do that for a continuous function. And so if we're going to average over the surface of the sphere, the logical definition of the average would be to take 1 over the area of the sphere and then multiply that by the area integral of the potential. So the average of the potential over the surface of the sphere ought to be the integral of v dA divided by the surface area of the entire sphere, in other words, the integral of dA over the surface of the sphere. That's our definition of what we mean by the average. Okay with that? Happiness and joy? Happiness and joy?
Yes.
No happiness, no joy? Anybody? Folks seen integral averages before? Most people are saying yes, but some people are going. What's that? Are you serious about that? You've done it in quantum for sure, yeah. Yeah, I mean, if you average something, if it's a discrete quantity, you add them all up and divide by the total number of them, right? So if I'm going to average something over an area and it's a continuous quantity, then I add up all the little VDAs and divide by the DAs all added together, essentially, would be the idea there. And so we're forming an area-weighted average of the potential. And we're on a sphere, and so our area element, because the sphere has radius big R, is going to be r squared sine theta d theta d phi. Since we're in spherical, we'll just put spherical coordinates on the surface of the sphere. And meanwhile, our beloved law of cosines. Never thought you'd use the law of cosines as much as you do in this class, huh? It's just everywhere. The beloved law of cosine says that script r is equal to z naught squared plus r squared minus 2 z naught times r times the cosine of theta, all square root of all of that, just using the triangle that involves Q, the origin, and the little patch. And script R is opposite angle theta, so the law of cosines gives us this for the length of script R. So, I heard that. I didn't see who did it, but I heard it.
It was Corey.
It was Corey? No, it was coming from this direction. At least that's what I thought. No. All right, anyway, the average over the sphere. I can always review the tape. The average.
Well, no, but you don't know who did it.
I don't know.
So-
Right?
You're
You know, you see, if we do a careful frequency analysis in terms of Fourier components, then we'd be able to, you know.
You're gonna
do
pin
some
down the
things.
voice.
Yes, that's right. I'm going to do a voice print analysis because it's that important to me to know who won. Okay, so we want to do that integral right there. And what we can do is an integration by substitution because, no, we're not just going to be silly people that run right to Mathematica in this situation, although we will in a minute. So mu is equal to the cosine of theta, d mu is equal to the minus of sine theta d theta, and for the limits, mu of 0 is equal to 1, and mu of pi is equal to 0. So that turns that into, after you do the integral on phi and turn it into a 2 pi, then that turns it into 1 over 4 pi q over 2 epsilon naught times the integral from 0 to 1 of mu d mu over z naught squared plus r squared minus 2 z naught r mu to the 1/2 power. And, okay, there, throw Mathematica at it unless I'm missing something. You know, I could be, but did you guys all get the memo though? You know, so in general, if you're doing a homework and you get to an integral and you use Mathematica when you could have done it by substitution or by parts, then yes? Cosine of pi is in fact -1. Yes? Right, so, yeah. Yeah, -1. So, oh, bad. Let's see, so this is going to be then, right, so it would be then 1 to -1, but there's a minus sign right here, so it becomes -1 to 1. Does that sound right? That's right. Happiness, not happiness, okay. So then that's going to be 1 over 4 pi q over 2 epsilon naught. And so then we're going to have to do z naught squared plus r squared minus 2 z naught r mu to the 1/2 over z naught r, evaluated between -1 and 1. And so, and then I think I went ahead and did it right when I actually substituted in, but then yet I still wrote 0 and 1 in my notes. But I think what I've got written for the next line is nevertheless correct. 1 over 4 pi q over 2 epsilon naught z naught times r. And then when I put in mu is equal to 1, I'm going to get z naught squared plus r squared minus 2 z naught r. And that is equal to z naught minus r squared, and then I take the square root and it turns into just z naught minus r, or z naught, yeah, z naught minus,
Yeah, I was going to ask you, because right there you already have the r squared canceled out, but in here when you substitute it in,
yeah.
there's no r squared in the numerator. Of the
Let's see.
you know, like when you put d again in, wasn't there supposed to be like r squared sine theta?
Just a minute. Okay, let's see. So this, that's going to cancel that
Yeah.
r squared,
But
right?
not in there. Like, never mind.
No, is that, okay, so,
Yeah, they cancel out there, but they don't cancel out here until the end.
what
Then
does,
it'll
okay, well, wait a
exchange.
minute, okay. But see, I think that this integrates to this,
Okay.
okay? So I think, this integral is, I think, what I'm claiming here, as far as that's concerned, I think. Now I have to go check it. All right. So, and limits are right, minus 1 and 1. So, but then that's going to give me z naught minus r minus z naught plus r, and that's going to give me a minus sign that I don't want. Yes?
Don't you need a minus sign when you substitute d to
I thought I did that by flipping the limits already. Let me think here. All right, so mu of 0 is, so it would be 1 to minus 1, right? And then it's going to be
okay.
minus mu d mu, 1 to minus 1. So if it's mu d mu, it's minus 1 to 1,
All right.
right? Any insight here, lovely wife?
I need a piece of paper.
You need a piece of paper? Yeah, there's something back there.
I don't have anything to write with you.
All right. Oh man, that's annoying.
You could just sort of like that.
Yeah, we could, right. Or I could just say, anyway, when I fix the notes, or when you look at it more carefully, what it will eventually turn into, because I don't want to spend half an hour trying to fix this.
So we're fixing page 72 and
Yeah, I'm fixing page 72 and page 62, apparently. Yes, all right. So, all right. That's nice to have on tape for posterity. Anyway, I think it turns into z naught plus r and minus z naught minus r if you do it right. So then the z naughts cancel and you get 2r out of that, so that'll cancel this 2r. And so what you'll get then is that the average of d over the surface of the sphere, and I know this is what you get, it's just how do you actually get it, is q over 4 pi epsilon naught z naught. That is what you do get. I know that to be a fact. That's what you get if you do it all right. But the thing to notice is that is, in fact, the potential due to charge q at the center of the sphere, because it's a distance z naught away, and the potential is charge over 4 pi epsilon naught times distance from the charge. So this is, in fact, v at the center of the sphere. Exclamation point. And so, in other words, we have what we wanted. That the average of the potential over the surface of any sphere, because notice we didn't say anything about the radius of the sphere here, it canceled out. The average of the potential due to a point charge over any sphere is equal to the average, is equal to the value of the potential at the center, as long as the sphere doesn't have q inside of it. This is, we did assume that q lay outside the sphere. So as long as q is outside the sphere, the average of v over the surface of the sphere is equal to the value of v at the center. Are you happy with that, Rachel?
Yeah.
Yeah, okay.
That's good.
Right. So we have that equation. I didn't have a symbol for joy. So. Right.
Put two smiley faces on
Huh?
top of each other. Two
What?
smiley faces on top of each
On
other.
top of it was that joy.
Yeah.
Oh, okay. Okay, so here's. So there's joy.
Yeah.
And that's infinite joy. Okay. think I'm here. I'm rebooting. All right, there we go. So, corollary.
Really using Windows instead.
Which we've already, wait, we already said this too. Crap. But we didn't do this, right? No, we didn't do this before. I remember having gone through that
No, we
integral.
skipped it,
Yeah, we would have skipped corollary. It's still true.
Instead of longer. Yeah, you really
Yeah,
should read it.
it's still true that B has no local minimum or maximum.
You should write longer.
Yeah, no longer minimum or maximum. I actually did fix that in notes already, yeah, the new PDF, it has been fixed. All right. Off to a rousing start here. Or in other words, that any max or minima have to lie on the boundary of the region in question. And by the way, we showed that the potential of a point charge lying outside a sphere, its average over the sphere is the value of the center. And then, for any distribution of charge outside of a sphere, you can think of it as the sum of a bunch of point charge potentials, right? Potentials additive. So you could do a sum of a bunch of point charge potentials. If it's a continuous distribution, you're integrating over a bunch of little diffuse potentials. So the fact that it works for a single point charge implies by superposition that it works for any distribution of charge outside the sphere. So for any region of space where Laplace's equation holds, where there's any region of space which has no charge in it, any point in that region, you could draw a small enough sphere around it that all the charge lay outside that sphere. And so this property of Laplace's equation will hold. And so it follows that for any region of space where Laplace's equation holds, any maxima or minima have to be on the boundary of that space. In general, Laplace's equation doesn't hold everywhere in the universe because that would be a charge for the universe. So there's always boundaries on any region where Laplace's equation holds. Does that make sense? Okay. See, I'm paranoid now about the happiness quotient because of what happened last time. So, what? Sorry. No. You don't have to apologize because you're the person who actually solved the problem.
Ooh.
That's right. That's the
I'm
good
sorry,
person.
Dr. Harmon.
It's okay, Steph. I do forgive you. Yes, I just wish everyone could be more like Yasser and speak up when there's a problem.
Oh, hello.
Anymore.
Okay, so now let's make more precise what I've been hand-waving before, and cause Steph anxiety about, where I just kind of say, if we can find a solution and it works, it's the only one, woo! Okay, let's be more specific about what we mean by that. The first uniqueness theorem. This says that the solution to Poisson's equation within any volume is uniquely determined if the value of V is specified at all points on the surface bounding this volume. Yes?
I figured out what you did wrong in here.
Oh, you did, huh? Oh yeah, what did I do wrong?
It's because when you take the integral, there's a minus sign in front of the 2z not r. So there's another minus sign, which means you need to flip the limits again.
Oh, really?
Yeah, so then if the minus one's on top and the one's on bottom, then it works out.
Oh, okay, so it should have been, okay. All right, I'd have to see it because I'm not visualizing anymore where that, but, so there is another minus sign in there that saves the day.
Yes.
Okay, thank you. So I will fix that in the notes and then all will be sweetness, harmony. Okay.
That's correct. You did another line.
Oh, that's correct, so you can verify that.
Yes, that's right.
Oh,
Yeah, all
that's a quick verification.
right. Yeah, that's right, okay, good. All right, so I'll have to show me that later. All righty, so, right. Now the surface at infinity can be part of the boundary if you like, so that can be quite convenient. And so in general, the idea then is that you could have some situation where, say, you knew V on all three of these surfaces, and so there's no charge in this area, this volume really between the surfaces. The assertion is, if I know the value of V at every point on all the surfaces that bound the charge-free region in question, if I know V as a function of position on all those surfaces, then there is one, then the solution is uniquely determined. If there's a solution, there's only one of them. There can't be two solutions of Laplace's equation that satisfy the same boundary conditions, in other words. If you have a solution of Laplace's equation which satisfies the given boundary conditions, it is the solution of Laplace's equation which satisfies those boundary conditions. There aren't any other, or I should say Poisson's equation. But Laplace's equation is a special case of Poisson's equation. So this doesn't have to be a charge-free region, this is really what that means. So this is a great day here. So if you know the value of V on the boundaries, and you find a solution of Poisson's equation in some region, then it is the solution of Poisson's equation. We're not showing that a solution exists. That's a job for expert mathematicians. We're just assuming that a solution exists, and if there is a solution, it is the solution. Okay, does that make sense, what I'm saying there about that, what the assertion is here? Happy with that step or not happy, or not looking happy?
I believe it, I just.
Well, we haven't proved it yet, but the question is, do you understand what I'm asserting here?
You're saying if you know that, yeah.
Yeah, if you can find a solution which satisfies the boundary conditions, that's it. There's no other possibilities. That's what the assertion is.
I thought we were done.
No, we're not done, no. Right, yes. Yeah, proof. It is obvious. QED. Now we're done.
Great.
Right. Okay, no, it's actually not that obvious. So, proof. Suppose we had two solutions. Right? We're going to do one of these deals where we assume the opposite and show that it leads to something that can't possibly be so. So suppose that there are two solutions, V1 and V2. Right? What we're going to do is show that V1 minus V2 has to be 0. So we're going to everywhere in space. So if there are two solutions, then V1 and V2, then by the linearity of Poisson's equation, then their difference, V1 minus V2 equals V3, is a solution of Laplace's equation. So in other words, if I take grad squared of V3, well, the Laplacian is a linear operator, right? In other words, it's the second partial with respect to x plus the second partial with respect to y plus the second partial with respect to z. Well, the second partial with respect to x, say, of the sum of two functions is the sum of the second partials of those functions. In other words, this is a linear derivative operator. The derivative of the sum is the sum of the derivatives. The second derivative of the sum is the sum of the second derivatives. And this is just 3 second derivatives added together. So grad squared of v3 is equal to, well, that's grad squared of v2 minus v1, because that's what v3 is. But grad squared of v2 minus v1 is grad squared of v2 minus grad squared of v1. That's what linearity means, that the operator on the sum is the sum of the operator on the individual functions.
Isn't it B1 minus B2?
What's that?
Or B1 minus B2?
Oops, v2 minus v1. So, what, yeah, v2 minus v1. Yeah, sorry. Thank you very much. Yeah. It would have worked either way, but it should be consistent, certainly. Okay, well, by assumption, v2 is a solution of Poisson's equation. So grad squared v2 is equal to minus rho over epsilon naught at each point in space. And v1 is also a solution of Poisson's equation. So by assumption, grad squared v1 is minus rho over epsilon naught at every point in space. And since we're taking minus grad squared v1, that brings in plus rho over epsilon naught. And so those add up to 0. So v3 is a solution of Poisson's equation. Grad squared v3 is equal, of Laplace's equation. Grad squared v3 is equal to 0 at every point in space. So the difference of two solutions of Poisson's equation would have to be a solution of Laplace's equation. Okay, everybody on board? Still on the train here? Yes?
When you said grad squared v2 is rho over epsilon naught, where did you get that?
Because Poisson's equation is grad squared v is equal to minus rho over epsilon naught. That is Poisson's equation. And so, since v1 and v2 are supposed to be solutions of Poisson's equation in this region, it's automatically true that that has to be what their grad squareds are equal to. By the very definition of being a solution of Poisson's equation. However, it has to be true that v3 is equal to 0 at all points on the boundary surface. And remember, the boundary surface can be a composite of several surfaces, right? In other words, I could have, say, some spherical shell with some other surfaces inside of it, and I want the volume that's bounded by all those surfaces. When I say the boundary surface, I mean the set of surfaces which serves to enclose the volume, to define the volume in question here. So V3 is 0 at all points on the boundary surface. I say surface because I'm thinking all of the surfaces together as the single boundary surface, but it could be broken into several pieces disjointed from one another in space. Since it has to be true that V2 is equal to V1 at all points on it. And the reason for that is because we've got specified boundary conditions. By assumption, we know the value of the potential at all points on the boundary surface. And so, in other words, we're assuming that both V2 and V1 satisfy the boundary conditions. And remember, boundary conditions gets tiresome to write all the time, so I just like to say BCs for that. So V2 and V1 both satisfy the boundary conditions, so they both have that same value of the specified value of the potential at all points on the boundary, so their difference has to vanish everywhere on the boundary. Their difference has to be 0 everywhere on the boundary surface. So like if we had just a simple situation where here's the boundary surface, here's the region in between, and I want to solve the Poisson equation, I'm saying I know what V is at every point on the boundary. So if V2 and V1 are both solutions of Poisson equations with that boundary conditions, then V2 and V1 both equal that specified function on this boundary, and so their difference has to be 0 everywhere on the boundary. Does that make sense? See what I'm getting at there? Okay? All right. Now, we use the corollary. The corollary that said that a solution of Laplace's equation doesn't have any local maxima or minima. Any maxima or minima have to be on the boundaries, right? So V3 is a solution of Laplace's equation. All its extrema have to be on the boundary. All the extrema have to be on the bounding surface. But if the function is 0 everywhere on the bounding surface, and any maximum or minima have to be on the boundary surface, then what does that imply? It's got to be 0 everywhere, right? Because otherwise, you would violate that condition that any maximum or minimum have to be on the bounding surface. If the bounding surface is everywhere at 0, and 0 is as big or as small as the function can get, then the function has to be 0 everywhere. So that means that our two solutions, V2 and V1, do in fact have to be equal to one another, since V3 was their difference. Therefore, if you have a solution, it must be the solution. So if you can find a solution of Poisson's equation that satisfies the boundary conditions, you specify V on the boundaries, you're done. There can't be any other possibilities that you're overlooking, which is extremely useful, because that gives us the license to just be clever and dream up solutions to electrostatics, basically. And if we can dream up a solution that satisfies the boundary conditions, we're done. We don't have to worry that we're missing anything. Okay? Do we have happiness and joy? Corey's not saying anything. Yeah, I like that. That's a good happiness and joy symbol. Was that your intention, lovely wife? Was that be happiness and joy, or was that just joy? Because I think it should just
That
be
was
happiness.
just joy.
But I think that should just be happiness and joy, just the two of them on top of one another. Works for me. The word of the day is that.
Oh, you're doing a Prince thing.
Yeah, it's like
symbol.
Prince, that's right, yes. So this is the word of the day, and it's pronounced like this. Or no, it's pronounced like this. Okay, so, having proved our first uniqueness theorem, but wait, there's more. Equally useful is the fact that if I have a bunch of conductors, the only thing I need to know is how much charge is on each conductor. And that uniquely specifies everything. You know, if it's electrostatics, if I have a bunch of conductors and I know how much total charge is on each conductor, there's only one way that those charges can rearrange themselves, and only one constant electric field that could exist in that system, if it's in electrostatics. So in other words, when it settles down to electrostatic equilibrium, then there's a unique way for the charges to arrange themselves over the surfaces of those conductors that makes them all equipotentials and that thereby sets up a unique electric field in the space between the conductors. All I have to do is say what the charge is. There's no way that there can be multiple ways that the charges might distribute themselves over the surfaces in terms of the way the density varies from place to place. So that's a pretty powerful theorem. Second uniqueness theorem says, in a volume surrounded by conductors and containing some each containing let's see. Yeah. Yes. In a volume surrounded by conductors and containing some specified charge density, the electric field is uniquely determined if the total charge on each conductor is specified. There, that's what I wanted to say. In a volume surrounded by conductors, that was very nice. Like, surrounded by conductors. I already said it in a glorious way, so now I'll just write it. So notice that this is different from our first uniqueness theorem. The first uniqueness theorem didn't assume that the bounding surfaces belong to conductors. So it didn't assume that the bounding surfaces were equipotentials. Now we're assuming that the boundary surfaces are equipotentials because they're conductors. And all we know is how much total charge we've placed on each conductor. And in fact, why don't we just, we'll jump, I don't even remember if I put this in the notes, but it's certainly this example is in the book. Jump ahead to an example of the use of this, where you can use it to, assuming it's true, which we'll show in a minute, show something that could be kind of surprising. Suppose I have a situation where I've got two pairs of spheres like this, okay? And suppose that I put positive charge on this sphere and negative charge on this sphere, and negative charge on this sphere, and positive charge on this sphere, such that these two spheres both have charge plus Q, and these two spheres both have charge minus Q. Now, clearly, in this situation, if I put Q on this sphere, minus Q on this sphere, the charges are going to be attracted to one another, so they'll get some distribution of charge which looks like this, where the plus and minus charge will all crowd over towards the sides facing one another, because plus charge and minus charge, it's a big happy party, they love each other, they want to be together. If only I could put a wire between them, they want to discharge and all be one big happy neutral family. Same deal down here, okay? Now, suppose I do in fact put some wires in the system. I connect here to here with a wire, and I connect here to here with a wire. The question is, what happens? One possibility is, these plus charges and minus charges like being together, and these plus charges and minus charges like being together, so nothing happens. Everybody just sits there and remains one big happy family, as it was before. Okay? However, here's another possibility. Another possibility is that these charges just neutralize because it's plus Q and minus Q. And these charges just neutralize, plus Q and minus Q. So another possibility after I connect the system with wires is that everything discharges and everything becomes completely electrically neutral. Okay? Well, when I connect with a wire here, this system right here that I just drew a blob around becomes a single conductor with what total charge on it? 0. And this system becomes a single conductor, also with total charge 0. Is the situation I just drew a possible solution? Could you have a solution of electrostatics, basically, where you've got these two conductors which have 0 net charge on them, no surface charge anywhere, and no electric field anywhere? Is that a solution of electrostatics, of Laplace's equation, Poisson's equation? It certainly is. So therefore, it is the solution. That's the point. It is the solution. We found a possible solution, and so therefore it's the only possible solution. So without having to do any kind of detailed calculations like, does this situation really have lower energy than this situation? Because gee, these minus and plus charges like being together, blah, 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 blah. Without doing any calculations, uniqueness assures us that this very simple solution we dream up, let's just say it's 0 everywhere. If 0 everywhere works, it's the only possibility. So that's pretty powerful. This works, therefore it's the only possibility. Whereas if you didn't know the uniqueness, it wouldn't be obvious necessarily which of the two situations would hold. Are they really going to want to discharge? Yes, because discharging would give you a solution, but wait, if you've got a solution, it's the solution, QED, quite easily done. Okay? That's what it stands for. None of this Latin, you might have heard it stands for some Latin gobbledygook, quite easily done.
What is the Latin? You know what it is?
It's quito isilie donus. I don't remember.
I think it is quid est dictum.
You're probably right, yeah.
Think.
Which means, thus it is so, is that right? Or thus it follows.
Said, or something.
Thus, I
It's
think it's
written,
thus it
said.
follows, or thus,
Dictum
no, thus
is
it is
said.
said, something like that, yeah, I don't know. Thanks a lot, you had to ask that. I was thinking like, oh man, I hope nobody asked me what Latin actually means. But no!
I think the word demonstrate.
Oh, maybe you're right,
Thus it's demonstrated.
thus it's demonstrated, yeah, probably you're right, yeah.
I don't remember the other.
Yeah, I think it is quid est, is that right?
Yeah, I think
Quid
so.
est demonstratum or something like that, yeah. Let's go with quite easily done. Product placement.
I'm really thirsty for a Coke right now.
You should go get one right after class, Steph.
Can I do the?
Oh, that's right, yes. That was great.
How's it Coca-Cola Classic for you?
What?
How's that Coca-Cola Classic for you?
It's delicious, yes. You know, it's the cause that refreshes. It is a delicious Coca-Cola Classic. All right.
After 20 products like this.
That's right, yes. Yes. Yes, you know, these quartet erasers do a wonderful job of clearing the board of writing.
What's that board is that?
I don't know, actually.
Who makes the big eraser?
What?
Who makes the big eraser?
I don't know. But you know, this fine vapor eraser is also of terrific quality.
We do what we can.
All right, proof. So we'll draw some arbitrary looking funky system here of conductors. So this is supposed to be, here's this outer conductor and a bunch of inner conductors, and we're interested in the volume that is bounded by all those conductors, the stuff that's not inside the conductors. This outer, this outer surface could be a conductor at infinity, if we like, or in other words, you can let the outer conductor just be the surface at infinity, if you like, because what's going to be important when we make this proof is that even though we don't know what the potentials are on each surface, we do know that they're equipotentials. We do know that whatever the potential is, it's constant on each of these surfaces. For a finite charge distribution, is the surface at infinity an equipotential? Well, what do we let V go to as you go to infinity? 0. So the surface at infinity is an equipotential, so it's acting like a big equipotential conductor. So that's why you can take this and let this surface be at infinity, so that basically you just say, if I had 3 conductors in the universe and I knew the charge in each one, and that was the only thing in the universe, that would uniquely determine the electric field everywhere in the universe once it settled down to electrostatic equilibrium. And so that's what we'll do after you guys go see Linnaea or whatever it is.
Go ask Linnaea.
Wow, Nick, that looks delicious. What's that you're drinking?
It's a nice, just Coca-Cola classic.
Ooh, 20-ounce size.
Yeah.
Good choice. Roof. So, here's our picture that we got a bunch of conductor surfaces here. And what we're going to do is make a bunch of, well, we'll say that this one's got, say, Q1 on it, and this one's got Q2, Q3. In general, you call it Qi on the ith conductor. We'll make a bunch of cute little Gaussian surfaces. Well, they could be big. Our Gaussian surfaces are going to hug our conductors just outside of them. So, little dashed lines to represent our huggy little Gaussian surfaces that virtually coincide with the surfaces of the conductors themselves. They're epsilon away, where epsilon is as small as you like. And we'll even spend the next half hour making dashed lines around the outer conductor here, because there's also another Gaussian surface which hugs inside of that outer conductor, or the surface at infinity if you like. So Gaussian surfaces. So we got a key here. Dash, dash, dash is Gaussian surfaces hugging our conductors. And we'll do the same sort of thing we did last time, namely, we'll assume that there's 2 solutions and then show that their difference is equal to 0 everywhere. Assume there are 2 solutions, E1 and E2. So now we're talking electric fields here. E1 and E2. Then both of them certainly obey Gauss's law, like any self-respecting electric field. So therefore, and every electric field is self-respecting. Therefore, E1.dA, E sub I dot dA. So another, what am I trying to do here? No, E1.dA, silly me. E1.dA, let's say dA sub I to indicate that it's on the ith surface. All right, I have to put a special notation on the DVDs for this lecture. You know, it's like Dr. Harmon. Is what?
Greatest moment in quotes.
Greatest, that's right, yes. Or it's
Greatest quotes. Greatest in quotes.
Right, or how about, it's the electrostatics blooper reel. So, if I find the flux E1 through the ith surface, it's equal to the charge on the ith conductor over epsilon naught. And similarly, it's going to be true that the flux of E2 through the ith surface is same thing. Because if there are 2 solutions, both their fluxes have to be charged enclosed over epsilon naught. And since they're enclosing conductors, then it's the charge on that conductor over epsilon naught that its flux produces. So there's one of these for each conductor. both E1 and E2. Every conductor gets its own personal relation of that sort. We don't want to leave anybody out here. And, but wait, there's more. We can also, for the outer boundary, and remember, that could also be the surface at infinity too, that's a possibility. For the outer boundary, since the surface at infinity acts like kinetic potential as we just argued, whatever the outer boundary may be, E1 dot dA on that outer boundary must be the total charge on all the conductors added together divided by epsilon naught, because that surface bounds all the conductors and the charges on them. And of course, same deal for the flux of E2 through the outer boundary. And so, yes, Steph, would you like to share that with everybody? No? What's that? You're cold. Ah, okay. Now consider E3 equals E2 minus E1. For which the divergence of E3, well, divergence is a linear operator too. So that's the divergence of E2 minus the divergence of E1, but both E1 and E2 also have to satisfy the differential form of Gauss's law, which of course is going to be rho over epsilon naught is each of their divergences. So therefore, div E2 minus div E1 is rho over epsilon naught minus rho over epsilon naught is equal to 0 everywhere for the divergence of E3. And over each of those surfaces, the flux is going to have to be 0, because take any surface and the flux of the sum is the sum of the fluxes, and so therefore the flux of E2 minus the flux of E1 is Qi over epsilon naught minus Qi over epsilon naught is equal to 0. So E3 has no flux through any surface, and its divergence is equal to 0 everywhere. Any of the surfaces bounding the conductors, not necessarily from this through any surface, but certainly for any of the surfaces bounding the conductor, E3 has 0 flux through them, because it's the difference of E2 and E1, and those both have flux Qi over epsilon naught. Okay, happiness, joy, goodness, like, yes, no, okay. So, now what? Now, we invoke a lovely vector identity, because all vector identities are lovely. That's a crock. But anyway, vector identity. The divergence of V3 times E3 is equal to V3 times the divergence of E3. So this was, the identity is true for arbitrary scalar function and vector function, and then we'll apply it specifically to if the scalar is the potential associated with the electric field E3. So div V3 E3 is V3 div E3 plus E3 dot grad V3. Well, that's all fun to say with all those threes there. Div V3 E3 is V3 div E3 plus E3 dot grad V3. That's kind of fun. I enjoyed that. Now, the divergence of E3 we just saw was equal to 0. And meanwhile, the gradient of V3 is minus E3, because when you got potential, the electric field is minus its gradient. So therefore, grad V3 is minus E3. And so, in other words, what we find then is E3 dot minus E3, which is minus E3 squared. So div V3 E3 in the end is minus E3 squared. The magnitude of E3 squared. Two, 4, 6, 8. Now it's time to integrate this over all the volume outside conductors. In other words, the region where we're interested in is the region outside the conductors. And apply the divergence theorem. Our friend, the divergence theorem comes in here. So, we can say that the integral of div V3 E3 d tau by the divergence theorem, that integral over all the volume bounded by the conductors is the integral over the whole boundary surface, which is in multiple parts here. It's okay for the surface bounding a volume to have multiple pieces to be disconnected. So in other words, it's got this outer piece and the three, in this case, inner pieces surrounding the conductors, right? You got what I mean there? The boundary surface is multiply connected, or whatever. What's the math term for that? Do you remember, Danielle? Do you know? Okay, it's a bunch of different parts. All right. Anyway, is the divergence of V3 E3 is, of course, the flux of V3 E3 over the boundary surface. And by this relation that we just derived up here, that's also equal to the integral of E3 squared d tau. Okay. Excuse me. So now, and notice here that if we were looking for the n hats, n hat always points to the outside, quote unquote, or in other words, you're pointing into the volume everywhere in these integrals. Now we invoke the fact that we know V3 is constant on each conductor. How do we know that? How do we know V3 is a constant on each conductor? They're conductors. Yeah, damn it, they're conductors. They're equipotentials. Right?
It is obvious.
Yeah. It is obvious, yeah. Because they're equipotentials, parentheses, duh. Close parent. Could be a different value for each one. Could be different for each one, but it's something. All the value on the ith conductor V3I. V3 on the ith conductor, V3 sub I. Then, if I take that integral over the bounding surface of the flux of V3 E3 dot dA, well, that's the sum of the fluxes through each piece of the surface. So I'm going to say, let's add up all the fluxes through each ith surface there. So SI is the ith surface. V3I E3 dot dA. But since V3I is a constant, it can be pulled out of the integral. So we get the sum over I of V3I times the flux of E3 through each surface. So you sum V3I times flux of E3 through the surface. Oh, but wait a minute. The flux of E3 through every surface is 0, because E3 was the difference between two vectors whose fluxes were equal to Qi over epsilon naught, so their difference gave 0. So that all adds up to 0. Since E3 hath no flux through any surface, adds up to 0. But wait a minute. That means that this is equal to 0. Because what we're getting right here, this flux of V3E3 through the whole bounding surface, we also showed was equal to minus the integral of E3 squared d tau over the volume. So the volume integral of E3 squared is equal to 0. Can E3 squared ever be negative? No, unless E is complex, but we don't allow complex electric fields. So this is positive definite, right? It can't be negative. So if some quantity which can't be negative at any point integrates to 0, what's true about that quantity? It's 0 at every point. Since E3 squared is greater than or equal to 0, this implies the fact that its volume integral is equal to 0. This implies E3 is 0 identically. E3 is equal to 0 at every point. Therefore, E2 is equal to E1, because E3 was E2 minus E1. Therefore, E2 is equal to E1. So if there are two solutions, they are identical. In other words, there's only one solution. And so we have what we want. So, again, if you know the charges on a bunch of conductors, and you can dream up a solution, it's the only possibility. And we already gave that example of how that could be useful for those pairs of spheres next to one another. That tells you if you connect them with wires, they're going to discharge, because clearly two neutral conductors is a solution of electrostatics. And so since you dreamed up a solution, you just said, oh, wonder if this would work. And you say, well, I guess it will. And then you say, but I got my uniqueness theorem, so it's the only possibility. And so then you're happy as a lark after that. Okay? So I like that. I like to get to say, like, well, I guess that's only going to be the only possibility. You know, that's very satisfying. So I hope you like that too. It's lovely. It's wonderful. All right. Happiness and joy. I'm going to assume happiness and joy, unless somebody stops. Yeah. Okay. All righty then. Now. This is a chapter about special techniques. So next we'll do a really cool special technique. Did you guys ever talk about image charges in 111? Where if you got, say, a point charge above an infinite conducting plane, you can figure out what the field looks like by making a clever guess and saying, hey, it works, it's the only possibility. All right?
I don't know.
Maybe, maybe not. So you'll decide whether you've seen this before based on seeing it now and saying, oh yeah, or, oh, never saw this before. The method of images. So we'll do the classic, simplest possible case, and then I'll give you a problem where you got to be a little clever. But the idea is, here's the classic application. Assay application. Find the potential and electric field everywhere above an infinite grounded conducting plane with a point charge Q suspended a distance d above it. Everywhere above. And, there we go, infinite grounded, because it's been bad, grounded conducting plane with a point charge Q suspended a distance d above it. What does grounded mean? What does it mean to ground something? Yeah, it means basically set its potential equal to 0. In practical terms, when you ground a circuit, you connect it to the earth because the earth has enough water in it that's in the soil that's a pretty good electrical conductor, and so the earth is a pretty decent equipotential, and mineralized water, pure water is not a good conductor. But anyway, earth is a pretty good equipotential, so you just set the earth's potential equal to 0 rather than 0 at infinity, and you ground your circuit by, for example, like what's a way to ground a circuit? You guys ever talk about that? What's that? Well, so for example, you know, if you connect a wire to a cold water pipe, and it's a copper pipe, you'll ground it because copper pipes go into the ground, and so they're touching earth, and so they basically get earth potential. So you can ground something by connecting it to a cold water pipe if it's copper. The third prong in an outlet is a ground wire. It's literally connected to earth in order to ground things and keep you from getting shocked. Ultimately, is what they're there for. You ground for, if you have a dryer, for example, or a washer, you connect the outside of the metal to ground so that if something happens and the wiring inside gets messed up so that one of the live contacts touches the outer shell of the washer, well, that would be bad because if you touch it, bzz, as a result of that, but the ground wire connected to the outer shell means that if that happens, now the current will flow to ground and basically blow a fuse instead of causing you to get shocked by touching a surface that's a high potential. That's what ground wires are for safety. Anyway, we've got a grounded conducting plane with a point charge above it. So, and it's infinite. So I'll draw a side view here. I don't know what I got in the notes here. Here's my grounded conducting plane. So that's the ground symbol like that. That's the symbol we use to say that something's been grounded. And here's our point charge Q. And it's a distance d above the plane. Okay. What do we know about the electric field at each point on the surface of a conductor? What's one thing we can always be sure about? The electric field at each point on a conductor. It's, yeah. It's perpendicular to the conductor's surface, right? So we know that the field lines have to come in perpendicular. Now this is a positive charge, so the field lines point towards it or away from it? Away from it, right? So we know qualitatively the field lines are going to look something like this. They're going to have to come radially out of it, but then when they land on the conductor, they have to be perpendicular to it. So something like this is what the field lines look like. All right, I can do a better job. Anyway,
It's a pumpkin
it's a pumpkin, that's right, yes.
sitting in the ground.
Yes, okay. Now, remember, we've got a uniqueness theorem which says if we can dream up a solution and it works, bingo. It's the only possibility. All right? Can you think of a configuration where you'd have the field lines everywhere perpendicular to some plane, and the field lines go to the point charge like that? You have to charge the plane. You're certainly right. There's going to be negative charge density on the plane. Yeah, it's going to end up having minus q total, as a matter of fact. Now, this is the method of images, so that's a hint.
There's a mirror image.
Think of it kind of, yeah, could you mirror image this? What would happen if you mirror imaged this field? What would you have produced? Yeah, yeah. If I make the mirror image of this field, if I just mirror image it down here, then, in other words, I let all the field lines come back together, like so.
Oh, wait, this is the train, right?
They come all back, you know, a crappy drawing, but okay. They all come back together. They're all flowing into something down here. What would that something be? A minus q charge. So in other words, we say, what if I just said, what happens if I put a charge minus q, if I remove the plane, I pretend the conducting plane is not there, and instead I consider a charge minus q down here. Then what situation will we have? We'll have a situation where the field lines are all perpendicular to the plane, just like they need to be. Not only that, let's see, will it be true that this plane is an equipotential? And, you know, forgetting that it's a conductor, just the 2 point charges, is this plane an equipotential? It is, because if I move along the plane, the direction of the electric field is perpendicular to the plane. So if I move along the plane, how much work is the electric field doing? None, right? Because the force will be perpendicular to the motion. So the plane is an equipotential. And so I've got a situation where certainly I can set the potential equal to 0 on the plane because it's an equipotential for these pair of point charges. The plane's an equipotential. It can have 0 potential. In fact, that works because you go off to infinity and the potential will stay 0. So that satisfies the condition that the potential goes to 0 as you go out to infinity, and that the potential is 0 on the plane. But then wait a minute. So the electric field of this pair of point charges above the conducting plane satisfies all the boundary conditions. It goes to 0 as you go to infinity, and it's equal to 0 on the conducting plane. So by miraculous cleverness, we've dreamed up a solution which works above the plane. It satisfies the boundary condition that the plane's an equipotential, and furthermore, the potential can be set to be 0 on the plane, and if you do that, the potential goes to 0 at infinity. So we've solved the boundary conditions with this solution we just dreamed up. And what do we know about this solution that we just dreamed up? That it satisfies the boundary conditions, and therefore, it's the only possibility. So in other words, this is the correct answer. Now, obviously, this part isn't right down here. This isn't satisfying the boundary conditions below the plane because the plane's supposed to be an equipotential, and certainly an actual charge down here, you wouldn't have this being an equipotential. We don't care about that. We only care about above the plane. The solution works above the plane. And voila, that means it's the solution above the plane. So in other words, an image charge does the trick. And so it's kind of obvious why we call it an image charge. It's kind of like, you know, an image of the charge up there.
So we're saying the charge on the plane doesn't exist.
It doesn't actually exist. It's not there.
But what is there recreates what's
That's right.
drawn above.
Yes, that's right. Putting the negative charge down here recreates the right field up here, because the field of this configuration works above the plane. The plane is an equipotential. The electric field is perpendicular to it everywhere, just like it needs to be, so the plane is an equipotential. And if I set V equals 0 at infinity, automatically the plane has potential 0, because I can come in along the plane from infinity and never do any work. So V is equal to 0 on the infinite half hemisphere, infinite hemisphere if you like, consisting of the infinite plane plus the surface at infinity. V is equal to 0 everywhere on that boundary. That's the boundary condition, right? And then you could also, if you like, think of another boundary condition as letting this charge get smaller and smaller. You know, think of it as not a point, but as something a little bit bigger than a point. You know that as you got closer to it, the potential on it would have to be the charge divided by 4 pi epsilon naught times its radius, and certainly in that limit, this does what it has to do. In other words, it approaches the field of a point charge on the point charge. So all the boundary conditions are satisfied. Since this solution works above the plane, it must be the solution. So we throw away what's below the plane. We know that it's not really there, but the solution of the plane works. It satisfies all the boundary conditions. Therefore, it is the only possible solution. So it's almost like it's a miracle. You know, solving this from first principles, we'll have fun with that. But solving it by this clever trick, ooh, right? So this is applying the principle of working smart instead of working hard. You know, it'd be really hard to solve this from first principles, but with this clever trick, it's like, voila, we're done. Ooh, ah. Right? Happiness?
It really does look like a pumpkin.
What's that?
It just looks like a pumpkin.
It does look like a pumpkin, yes.
Arrow.
Right. So, gee, that's magnificent. How cool is that?
Dr.
Now-
Harmon.
Yes?
It's electromagic.
It's electromagic, that's right, yes. Why, we're a bunch of electro-magicians.
Yes. There's the mirror. I see it.
Yeah, that's right. And notice then, you know, this will work for anything, right? In other words, if you have a bunch of point charges, just mirror them below it. You know, change their signs and mirror them below it. And if you've got an infinite plane, it's just the mirror principle here works. Now, you can have a more complicated situation, like if you have a sphere and a point charge, and I'll let you go through the example in the book, but they work out. Suppose I've got a sphere and a point charge outside the sphere. Well, now it's not so clear exactly where to put an image charge and what its value would be, but you do know one thing. And you don't always know an image charge will work, but you just say, okay, can I make it work? If there is going to be an image charge that will work, what can you say about its location?
It has to be outside.
It'll be inside, actually, it turns out. Yeah, it will be inside the sphere.
Because what about if you put a minus charge inside that sphere, you end up having.
Now notice it doesn't have to have, if this is Q, the image charge isn't necessarily minus Q, it might be minus some fraction of Q or.
Are you only worried about the outside of the sphere?
Only outside the sphere, right. So we can't put an image charge outside the sphere because clearly if there was an image charge outside the sphere, field lines would converge on that image charge. But a conductor and a point charge, they're not going to have that happen. The field lines aren't going to come to some point like that. So it's going to be inside the sphere. What I'm saying is, I don't want you to tell me exactly where it is. I want you to give me a restriction. In other words, could the image charge possibly be right there?
Sure.
No, why not?
Because then it would
Because it wouldn't
be
come into the sphere perpendicular.
Yeah, or another way to put it is, if I could put it there, would there be any reason I couldn't put it there?
It's not unique.
You couldn't get a unique solution, right? Because every point on a circle would be symmetric around the axis, and so any of them could work, but the solution's got to be unique. So it's got, well, not necessarily dead center.
The Q axis.
It has to be, right, it has to be on the line through the center of the sphere in Q. You can say that much, it has to be on that line. So then what you do is you say, okay, I'll just say it's some certain distance from the center which I need to find, and the value of the charge is some certain value which I need to find. And so then you say, okay, the total potential of the two charges has to add up to a constant over the surface of the sphere, and that then allows you to solve for where to put the image charge in order to make the sphere surface an equipotential, which you could set to be 0. So you say, let's let the sphere have potential 0. I'll put this charge inside of it, the negative charge. Can I find some value of its position and charge such that I can make the surface of the sphere an equipotential? And the answer is yes. So you can, it's in the book. You can work through the example of how to do that. I'm not going to do that here. I'll let you read all about that on your own. Yes?
I don't understand exactly what are these solutions to?
The solution is you got a point charge above an infinite conducting plane. Find the electric field everywhere. Find the potential and the electric field everywhere.
I don't understand why you draw an image charge.
So the idea is that we start off saying, okay, whatever the solution looks like, we know that the electric field is perpendicular to the plane at every location. Right? That's just on first principles. The electric field is perpendicular to a conductor. And certainly I know that the field lines converge on Q. If you get close enough to Q, the electric field has to look like just the field of that point charge. So I can qualitatively draw electric field lines coming away from Q, and I know they diverge from Q symmetrically, and then when they land on the surface, they have to land perpendicular. So just qualitatively, I could draw that sort of pumpkin-y looking thing as the electric field configuration. And then I say, okay, is there some other system that would have an electric field such that the field lines converged on Q and were perpendicular to the plane everywhere? And I say, oh, well, yeah, if I put a charge minus Q, the distance d below the surface of the plane, in other words, I eliminate the plane for the time being in my thinking. Let's say the plane is the xy plane and the charge is along the z-axis. If the charge is at z equals plus d, if I put a minus charge of the same magnitude at z equals minus d and drew the electric field configuration, well, it would be the mirror image of the electric field configuration above the plane, right? So certainly plus q minus q, this is what their field configuration would look like. And then you say, all right, that field, if I look at it above the plane, it does everything I need it to do. It's perpendicular to the surface at every location. The field of plus q and minus q combined is perpendicular to the surface at every location. It becomes the field of a point charge very close to the point charge. And the potential goes to 0 at infinity. Certainly the potential of this pair of point charges goes to 0 when you're infinitely far away from it. And it's a grounded plane, and certainly the potential is equal to 0 everywhere on the plane, because if it's 0 at infinity, and I come in along the plane, the electric field is always perpendicular to my motion, so therefore the line of integral of the electric field is 0, so there's no potential difference between the plane and infinity. So then if you like, what we've got is a situation where we have found a solution which does everything we want it to do. Think of this as extending out to infinity, and V is equal to 0 everywhere on this surface. The conducting plane and the hemisphere at infinity, V is equal to 0 at every point. This solution of plus Q and minus Q has that property. V is equal to 0 on the infinite hemisphere and the conducting plane. And the field approaches the field of a point charge at plus Q, like it needs to. So we found a solution which satisfies the boundary conditions, in other words. But wait, the uniqueness theorem says, if by hook or by crook we find any solution which satisfies the boundary conditions, it's the only solution. So therefore, even though we just made this up out of whole cloth, it works above the plane, it satisfies the boundary conditions, therefore it's actually the unique correct solution above the plane. So that's the power of the uniqueness theorem, and the power of this imaging solution is, in many situations with sufficient symmetry, you can just dream up, if you've got a point charge, you can dream up another point charge that will make the conductor surfaces an equipotential. And if you can do that, it's the only possible solution. Yes?
So if you were to write E of xy equals for those 2 point charges,
Yeah.
the solution that it gives for any, if y.
Yeah, like if I go to this point, if I want to know what's the electric field at this point right here, I just add up the electric field of minus Q and plus Q at that location.
Okay, but that's only valid above.
It's only valid above the plane, right? Below the plane, it's not a valid solution because, you know, suppose this is still a conductor down here. Well, the electric field vanishes inside the conductor. So yeah, it's an important point. The solution only works above the plane because it only satisfies the boundary conditions above the plane. It doesn't satisfy the boundary conditions below the plane, because below the plane, the boundary condition is the electric, below the plane, the electric field vanishes everywhere. So clearly, it doesn't work below the plane, but it works above the plane. So yeah, every location, the electric field and the potential are exactly what they would be for plus Q and minus Q. Just use them to calculate it. At every point above the plane, that works perfectly well. Yep. In particular, if you're on the plane, suppose we're on the plane. Here's our conducting plane. And here's some point on the conducting plane. And here is Q. Here is minus Q. So there's our script R there. And since we're on the plane, it's also script R for minus Q. Here's distance away from the line from the point charge down to the plane. So just call that R the distance from the center, if you will. Then, if I add up the electric fields, then the field of plus Q looks like this, so we can call that maybe E plus, and the electric field of minus Q has the same magnitude, but points in that direction. So there's E minus, and we're supposed to have the actual same magnitude. What's that?
You're right, E. It's like super E.
It's super E. Yes, it is. That's super E. It's E. Yes. Right. The parallel components cancel. So to find E, if that angle's theta, so that angle's also theta, E is only in the, if we let this be the Z direction, E then is going to be minus 2Q over 4 pi epsilon naught script R squared times the sine of theta times Z hat, 2 because there's 2 charges, and minus because it's obviously the sum points downwards. And the sine of theta is equal to, since it's d above the plane, the sine of theta is just d over script r. So this is 2q over 4 pi epsilon naught script r squared d over script r z hat. But r is equal to square root of, script r is equal to square root of r squared plus d squared to the 1/2. So E is equal to minus qd over 2 pi epsilon naught times r squared plus d squared to the 3/2, sorry, z hat. So that's the electric field as a function of position along the plane. Only depends on r. So if you put polar coordinates on the plane, the electric field clearly is symmetric, has circular symmetry, so it only depends on distance from the projection of Q onto the plane. And then knee-jerk, at the surface of a conductor, how's the electric field and the charge density related to one another? You want to get this to a knee-jerk reaction, you should remember this. At the surface of a conductor, charge density sigma, the electric field in magnitude is equal to sigma over epsilon naught, right? If it were an infinite plane, not a conductor, sigma over 2 epsilon naught on both sides. But if it's a conductor, 0 on the inside, sigma over epsilon naught on the outside. That should be instant. You should just remember that. You should not have to be reminded of that. So therefore, sigma is epsilon naught times the magnitude of the electric field. Or in other words, sigma is equal to minus qd over 2 pi r squared plus d squared to the 1/2. That's the surface charge density as a function of position. So we found exactly how charge piles up on the infinite conductor. Again, that'd be hard to do if you didn't think of this clever solution of using the image charge. If you want the total charge, we've got circular symmetry, so we don't want to use r d theta as our area element. You certainly could, but what you should use, just like for a sphere, you'd use d tau is 4 pi r squared dr. If you're doing area elements with circular symmetry in polar coordinates, you want to use as your area element a little ring whose area dA is equal to 2 pi r dr, circumference times thickness. So if I want the total charge on the plane, I have to integrate sigma dA. Is going to be, the total charge will be the integral of sigma dA over the whole plane, because sigma dA is dq. The amount of charge in our little ring is going to be sigma dA. dq is sigma dA, so I integrate sigma dA, so that gives me minus qd times the integral from 0 to infinity of r dr over r squared plus d squared to the 3/2, because the 2 pi r dr, the 2 pi's will cancel the fact that there's a 2 pi in the expression for sigma. So the 2 pi's cancel, and this gives me an opportunity to say, wow, a lot of people had this identical integral in a recent homework and used Mathematica for it. Ahem! Right? I was going like, ah, what are you people doing? Because the denominator has an r squared plus d squared. So of course what you want to do, given that there's r dr up there, if you see an r squared and an r dr, then, Nasser says, yeah. What's that? Then you don't use mathematical on that. You say u is equal to r squared plus d squared, and du is 2r dr, and then you say, oh look, it's a perfect differential. I can do this by substitution. And so you say, okay, then this is minus qd times the integral, well, you know, u goes from 0 to infinity again when you put in r squared is, u goes from d squared to infinity is what I should say. D squared to infinity right now, just because I didn't put that in my notes because I wanted to be able to say this here. So now I have to do this right here. So u of 0 is d squared, u of infinity is equal to infinity. So this is minus qd times the integral from d squared to infinity of du over 2 times u to the 3/2 power, right? And so u to the minus half, 3/2 integrates to what? 3/2 add minus 3/2 add 1, that's 1/2, so that's how you get minus 2, right? Times u to the minus 1/2. So you're going to get, now that's the disadvantage of because we're out of time here basically, but you get qd, so somebody stop me if I'm doing this wrong, times, is there a minus sign I'm blowing in there? No?
There's a minus.
No, that's right.
You're
No, I think it's
you're
right, yeah,
minus
so
2.
u to the minus half times, and then integrate between, or evaluate between d squared at infinity, and so infinity gives you 1 over infinity or 0, and d squared gives you 1 over the square root of d squared, or 1 over d, so you get minus 1 over d times qd is a grand total of minus q. In other words, the total charge on the conducting plane is in fact minus q, which is what you might have guessed in the first place. Yes, indeed so.
Oh my gosh. Oh my gosh, Roper.
All right,
You
so,
need to change that to a 3/2. Up, up, up.
where?
Right there, no, right, no, just with the sigma, that's 3/2. Up, no, up.
What? Oh, yeah.